Cranky Calculus. We are going to start talking about derivatives, which is a super important topic. Don't forget to like and subscribe for more content. Let's get right into this one. We're going to talk about today tangents, secants, and normals. So we first do know about secants. We should know the slope of a secant line. That's the same thing as f of b minus f of a all over b minus a. That's what you learned in pre-calc. What we're going to do now is we're going to take this, and there's a picture right here, but I'll explain this through Desmos here in a moment. If we want to find the instantaneous rate of change, we're going to try to take our secant line and we're going to try to minimize it. I'm going to show you what I mean by that. So here we have just some random curve, and I can find the secant line of this by having f of a, and then really it's going to be f of b. We can find the secant line right here by subtracting this. That's what this orange line is. It's just the secant line. Now, what happens if I take this second point and I move it closer to the initial point, the blue point? So now we still have a secant line, but as I go closer, that secant line starts to look a wee bit more tangent. You can kind of see it starts to line up right here. And if I go too close, Desmos is actually going to cut me off here. This is as close as I can get between the 2 points that Desmos allows me to. But it looks like a tangent line. If I were to zoom in a lot, which I will, you can see that it's still a secant line. It just appears to be tangent. All right, now, does that just happen right there in that part of the graph, or does it happen everywhere in the graph? Let's go ahead and look at that. Okay. So let's say that I'm going to move my point back over here. Does that happen again as I take this point and I go closer and closer to this other B point right over here? You can see that it starts to become a bit more tangent. Okay. As I move them closer and closer together, it appears to be more tangent. So what we want to do here is, instead of having a secant line or that distance between them, this little distance right here, we're going to call that h. We want to minimize that as much as possible. In order to minimize that distance as much as possible, we need to take the limit as h approaches 0. If we were to look at our instantaneous rate of change formulas, also known as the slope of the tangent line, also known as the derivative, you're going to see that we can get our slope function by this right here, which looks very similar to the secant line, which we have over here. But as I just showed, if we take our h and we minimize it as much as possible, that's going to give us a tangent line. So that's why this is going to be our derivative. So this is our derivative function. Okay. Now we have a super similar formula right here. This is the alternate form of the definition of a derivative. This right here is just the definition of derivative. So our alt form won't give us the derivative function, but it'll give us the derivative at c. So it'll give us the slope of tangent line at x equals c. Okay, so we have two different formulas we're going to use here that we have access to, which will tell us what the slope of the tangent line is, or we're going to be using this new big word, derivative. Pretty much almost all of calculus is derivative, at least the first half of the course. Okay, so as you're taking this course, if you don't know what to do, just take the derivative. It's a good chance that that's what you're supposed to do. So we're going to do this example. We're going to find the derivative of f of x using the definition of the derivative, which is going to be this one right here. So we're going to be able to find the slope of this tangent line. If I were just to go ahead and sketch this real quick on an axis, I mean, I don't know exactly what this thing looks like, but I do know it's a square root function. It looks like it gets shifted and a little bit more than that. But it looks like it's something like this. Okay? If I want to be able to find the slope at any point here, so I'm going to use pink. If I want to find the slope of this line right here, that tangent line, I need to know the derivative function. So let's go ahead and find that derivative function. So first thing I need to do in my equation is find out what f of x plus h is. So if I have f of x, then f of x plus h is going to be the same thing that I have right here, but instead of writing x, I'm going to write x plus h. And I'm just going to simplify that real quick, just for ease. All right, so I'm going to go ahead and use my formula right now. So f prime of x, which equals, I'll have this up here so you can see it, the limit as h approaches 0 of f of x plus h. I just found that, so I'm going to replace that f of x plus h with this root 2x plus 2h minus 1 minus f of x, which is my original function, which I had. And that is all over h. Okay? So if I were to substitute in as 0 right now, I would actually get 0 on top, 0 on the bottom, which is a big old no-no. So if you remember, whenever I have square roots, and I can just multiply by the conjugate, and everything will start to cancel out for me. So the conjugate here is going to be root 2x plus 2h minus 1 plus root 2x minus 1. So do that on top and bottom here. And then since I did multiply by a conjugate here, the numerator will simplify very nicely. And I'm just going to let the denominator just be. So those first square roots, because these are conjugates, are just going to knock out those square roots of each other. So I'm just left with, I can speak, 2x plus 2h minus 1 minus, those square roots are going to cancel out, but don't forget to distribute that minus sign all the way through. So that's minus 2x plus 1 to distribute. Okay? So that's how we get that plus 1, and this is going to be all over h. And then we have this big ol' ugly conjugate. And there we go. If you do notice, we have some things that are going to cancel out here. So I do see that this 2x is going to cancel out with this minus 2x. This minus 1 cancels out with that one. And I'm left with just a 2h on the top, which hopefully you notice that this is going to cancel out a little bit as well. So we're going to get 2h on the top all over this ugly looking thing right here. There we go. All right, h is going to cancel out. So now I'm left with just a 2 on the top. And I'm actually free to go ahead and substitute in my 0 now. So let's real quickly rewrite this. 2x plus 2h plus 1 plus root 2x. Oh, there should be minus 1s. I think I'm, oh boy, made an error here. I can fix this error. That should be a minus 1. That's just a copy error on my problem. It's a copy error, typo. There we go. So now when I substitute in the 0, which is totally legal, I'm going to get 2 over this right here is going to 0 out. So I'm left with the same square roots. So I'm going to get 2 of these same square roots. 2x minus 1, which simplifies to 1 over root 2x minus 1. That means that our derivative function is 1 over root 2x minus 1. Now, what in the world does this tell us? Well, if I were to substitute any value in, like let's say that I substitute in a 1, and let's say that that is 1 right there, that red line, we can find the slope of that red dotted line right there by substituting that into the derivative function, which is going to be 1 over root, what does that turn into? 2 minus 1. So this is 1 over 1. So that slope of this red dotted line is 1. And I can go ahead and plug in like a 5, for instance. And let's go ahead and find out what's going on at blue. Let's say that blue is right over here in this. Let's find the slope of that dashed blue line. So let's say that that is 5. If I were to substitute in a 5, I would get 1 over root 9, which is 1/3. So the slope of that blue line is 1/3. Isn't that so neat? Yeah, sure is. But with kind of pain in the butt, right? Totally get it. There will be shortcuts that we're learning very, very shortly, like right now, on how to do some of these things. So I'm going to show you real quick here is something called the derivative power rule. And it's actually on the next page right here. It just says that if we have any function that's a times x to the n, then f prime is going to be, you just multiply that n out in front, so it's going to be n times a x n to the minus 1. So we just subtract 1. Okay, so I probably made that sound more confusing than it actually is. If my function here is 3x to the 4th, the derivative function using the power rule would be 4 times 3, which is 12, and then subtract 1 from that 4. And your derivative function would be this right here. Only happens for polynomials, so that's all we got really right now. But what we can adapt this to as well is using our point slope formula. So we should know point slope formula from algebra 1. It's y minus y1 equals slope x minus x1. If we type this into calculus world, we're going to get y minus f of a, which equals to the derivative at a, x minus a. So hopefully you can tie in the similarities of those two formulas. And we'll talk about normal slope here in just a moment. So let's go ahead and get through this problem here. Kind of a physics-y problem, but we're going to go ahead and use it anyway because it's solid in terms of calculus. So a ball is thrown into the air with a velocity of 30 feet. Its height in feet after t seconds is given by 30t minus 16t squared. Find the average rate of change of the height of the ball from t equals 2 to t equals 3. Again, we're going to be using this average rate of change, which is the slope of the secant line formula right up there. So that average rate of change, average ROC, is equal to h of 3 minus h of 2 all over 3 minus 2. Okay. So when I substitute these values in, I'm going to end up with h of 3, I believe that is negative 54. So negative 54 minus h of 2 is negative 4 all over 1, which is going to give me an answer of negative 50. If I do want to give this some units here, this is going to be feet per second, because the h is feet, and the down here is the time, which is second. So this is feet per second. Okay. So what's happening between 3 and 2 is this thing is changing from at negative 50 feet per second. So let's just kind of pretend this person's throwing this off a really tall building or hill or whatever. Something. So this is going to look something like this. So that's why you're noticing here that our height is negative 50. It's below 50 from where the person is. But our average rate of change here is negative 50. Now let's go ahead and find our instantaneous rate of change of the height of the ball. So now that's going to be doing our derivative function. So we're going to do h prime of t is equal to, we'll use power rule for this one right here. So we're going to go term by term. So for the power rule for this t actually has a little 1 right here. We're going to multiply 30 times 1, which is just 30. And if you take a 1 away from 1, you get 0, and t to the 0 is just 1. Minus, multiply this 2 out in front, this 16, you're going to get minus 32t. Okay, that's just us using power rule right up there. Okay, so same idea. So if I substitute in a2 now, I'm going to get 30 minus, I'm good at math, 64. I'm going to get negative 32 feet per second. So this instantaneous rate of change is a bit more accurate than estimating the average rate of change. So this ball at this exact moment at 2 is falling at negative 32 feet per second. If you're finding the average rate of change between 3 and 2, it's a lot higher because, well, it's going to be changing a lot more at 3. Okay. So now we're going to take this answer right here, and we're going to find the equation of a tangent line, which again is above right here. So I need h of 2. I need h prime of 2. And then I'll have everything. So h of 2, which I did in the previous part, is negative 4. H prime of 2 is negative 32. We'll zoom out so you can see the formula. Right there in the upper left-hand corner is that calculus formula we have here for the equation of the tangent line. So I'm going to go ahead and do y minus, our value is negative 4, equals the slope, and then x minus 2. Okay, I'm just going to just stick with, actually, instead of x, my independent variable is t. Let's just go ahead and use t. All right, we can clean this up a bit. You don't need to clean this up, but it looks a bit nicer if we use this. Okay, And now our dependent variable isn't y. We actually use h. So I'm going to replace that y with h. So h of t plus 4 equals negative 32. T minus 2. Now, if you're doing this in a Fourier response question, you don't need to simplify it at all. But this is our note, so let's just clean this up, make this a bit nicer. So this is going to be h of t equals negative 4 minus 32 t minus 2. I'm actually not going to clean it up any more than that. That's good enough for me. You can show that negative 32. That's up to you. Now let's go ahead and find the equation of the normal line. So let's explain what the normal line means here. So we have this function right up here, and I kind of drew it, so I'm going to have it up here. So the tangent line at 2 is right here. So you can see that slope, that's a pretty large negative slope, which was our negative 32 feet per second. Our normal line is going to be perpendicular to that. Okay, which is going to be create a right angle. So to find our slope for a normal line, it's just the negative reciprocal. So for our slope of our normal line here, we're going to have n equals negative 1 over negative 32. So it's just going to be 1 over 32. That's going to give us our normal slope. And then from there, I can use our equation of a tangent line, which I have everything else from part C right in front of it. So we're going to go ahead and go with h of t plus 4 equals, instead of negative 32, it's 1 over 32 t minus 2. And just a little bit of a cleanup here. Negative 4 plus 1 over 32 t minus 2. AP Calculus doesn't really use much normal line stuff, but normal lines will appear into actual Calc 2 courses and some Calc 1 courses in college, and it certainly appears in Calc 3. So I just want to make you aware of what that is. And that's going to wrap everything up here very nicely. Going pretty simple here on our tangents, our secants, average rate of change, all that fun stuff. So don't forget to like and subscribe.